by the way. And you are going to present for us on huge antenna effects in all organic dye-based nanoparticles with highly efficient and ultra-fast energy transfer.
Thank you. Good morning, everybody. I'm Pietro Mancini, a PhD student from University of Perugia in Italy. And first of all, I would like to thank the organizing committee for giving me the chance to speak today. So, from a number... Okay, it's working. Sorry. So, from a number of evidences, it seems that the latter vesting phase in photosynthesis is assisted by quantum mechanics. In particular, the dyes involved in light harvesting have to exchange the exciton until it reaches the last acceptor at the reaction center. But this does not happen through a series of randomized dopings that would determine a large energy loss. But instead, it seems that the exciton remains in a quantum superposition state that allows to do a wave-like migration to the reaction center, and this accounts for the stunning high efficiency of the process. So, inspired by this, in a biomimetic approach, we try to apply an efficient energy transfer between dyes into a model system that we made by realizing nanoparticles from phenothiazine-based dyes. In particular, we selecting some dyes that are making energy transfer pairs, in particular an acceptor D and a donor D and two acceptors A1 and A2 that have been used to realize both single component nanoparticles or phones and binary alloy nanoparticles, B phones, through a nanoprecipitation method. In particular, stock solution in THF of the dyes is rapidly injected into a large amount of water under the vigorous ultrasound sonication provided by a probe-equipped processor. So when in water, the molecules find themselves into a bad solvent, so they spontaneously undergo into aggregation in self-organized particles. And when we made the single component phones, we have seen that there is quite a large spectral overlap between the donor's emission, the acceptor's absorption spectra. So we thought, okay, we can try to put the dyes together in a single particle to see if we can exploit an efficient energy transfer between the dyes. So we determined the quantum yield for the single component particles, obtaining the interesting value of 24% for the donor and the lower values of respectively 3 and 1% for A1 and A2. So we prepared the binary nanoparticles starting from a mixed stock solution of the dyes in which the donor is present in excess in respect to the acceptor, and from transmission electron microscopy, we saw that we have produced a spherical nanoparticle with a quite homogeneous size distribution with a mean diameter of about 40 and 36 nanometers for the A1 and the A2 respectively. And by collecting the absorption spectra in the same condition in a period of 2 weeks, we have seen that also there is a quite remarkable colloidal stability. Then we have recorded the stationary absorption and emission spectra for the binary nanoparticle. We have seen that, interestingly, upon preferentially exciting the donor at 370 nanometers, we only see an emission signal that seems to be the one of the acceptors with the only difference represented by a slightly blue shift. And this is interesting because the energy transfer seems to be quantitative. And despite the donor is both more concentrated and has a greater quantum yield in respect to the acceptors. This can be visualized also in the excitation emission maps, in which we see that no matter the excitation wavelength, only an emission signal can be collected. And as the first good evidence from this work, we saw also by determining the fluorescence quantum yield that the quantum yield of the acceptors get enhanced in the binary nanoparticle, reaching values of 8% for the acceptor 1 and 6% for the acceptor 2. So there must be some collective effects that determine this quantum yield enhancement of the acceptors emission in the mixed nanoparticles. Then we have determined the fluorescence lifetimes for the dyes, for the nanoparticle, both the single component and the alloy ones, by time correlated single photon counting. And the decays you see have multi-exponential shape, but this reflects the micro-heterogeneity of a nanoparticle sample. And the most remarkable evidence we can find from this data is when we look we collect the maximum of emission of the donor in the binary nanoparticle. We see that there is a huge quenching in the donor lifetimes. That so suggests for a very rapid, efficient energy transfer within the binary nanoparticles, with the lifetimes that seems to be dominated essentially by the lifetimes of the acceptors. Then from a previous investigation, we knew that HU is a dye capable of emitting delayed fluorescence. So we verified by applying TCSPC on a 2 microsecond time scale that this property is retained also in the single component nanoparticles with a good extent. But moreover, as the second valuable evidence from this work, also when we look at the binary DH nanoparticle, we see a certain delayed emission that is less important in respect to the case of the single nanoparticle, but nevertheless, this is still a very good evidence because, to my knowledge, is the first case that a delayed emission is seen after a quantitative energy transfer, and this could be very useful, for example, in bioimaging because it gives the possibility to doing gating time gated imaging, so removing the background from the tissue. And we performed nanosecond transient absorption experiment, and we have seen that, in fact, for the issue, there is a certain triplet state population that allows for a delayed fluorescence after a reverse intersystem crossing from the triplet to the single state. And regarding the fact that these delayed fluorescence have a lower importance, we think that since the emission is blue shifted in the binary nanoparticle and the single state has a greater energy, the singlet to triplet energy gap is large, and this has a detrimental effect because, in fact, the reverse intersystem crossing is more difficult. The kinetic constant associated with the process gets lower, and so we see a less efficient delayed fluorescence. So from TCSPC, we say that the energy transfer must be very fast, and we went in through of this by performing femtosecond transient absorption spectroscopy on the samples. Here I have reported the time resolved matrix, the 3D data matrix, the time resolved spectra, and the evolution associated spectra derived from the global fit on the matrix for the single component nanoparticle of the donor and the acceptor, as well as for the DA1 binary nanoparticle. We see that the signal for the donor is dominated by a broad excited state absorption centered at 670 nanometers, while for the acceptor we have a very broad excited state absorption between 550 and 750 nanometers with a ground state bleaching at 500 nanometers. Coming to the binary nanoparticle, we see an interesting behavior. In fact, both the matrix and the spectra seems to be dominated by signal only associated with the acceptor. So for giving an interpretation, we took a look at the evolution associated spectra, from which the only transient that seems to bear features relative to the donor is the first one that has been fitted with a lifetime of about 900 femtoseconds. So indeed, the energy transfer seems to be very fast and seems to happen in the sub-picosecond time domain. And we try to give an efficiency for the process by taking into consideration a Stern-Volmer model, so taking into account the lifetime of the donor in the single component nanoparticle and the lifetime of the quenched donor in the alloy nanoparticle, and we have obtained an efficiency for the process over 99%. Going to the donor receptor 2 nanoparticle, we can see that the behavior is the same, but if possible, is even more efficient. In fact, also in that case, is kind of difficult to follow the evolution of the donor into the acceptor. Is everything really fast? And if we take a look at the evolution associated spectra, again, the first transient that has been assigned to the energy transfer as a sub-picosecond lifetime, it has a lifetime of about 360 femtoseconds. So this brings the overall process even at a higher efficiency if we take into consideration a similar model. Then recently, we started also to apply pan-probe anisotropy to these systems. Here I have some very preliminary data that I show for DHU binary phones that were collected at 596 nanometers. And from this data, we can see as the anisotropy track for the system, starting from a value of 0.4, shows an ultra-fast decay that has been fitted with a lifetime of 380 femtoseconds. So is a lifetime very close to the lifetime that we have assigned to the energy transfer in the case of the magic angle femtosecond transient absorption experiment. And moreover, we also try to give an interpretation to this oscillation we see in the anisotropy track, and we have found by applying a fast Fourier transform on the residuals from the fitting, we have found a major peak in frequency at 1.7 terahertz that corresponds to an energy of about 56 centimeters to the -1 that could maybe account for some vibrational coherence that derives from the fact that the dyes are very tightly packed in the particles, so they are maybe in a strong coupling regime. But those data are preliminary and for sure needs for a better evaluation. For now, what I want to do a summary, we have prepared these nanoparticles named phones, and in particular, we have prepared the binary alloy nanoparticles by inspired models for studying the energy transfer. And this went quite good since in the binary nanoparticle we have a quantitative energy transfer with also an enhancement of the acceptors emission that accounts for maybe for this huge antenna effect and for some cooperative effect. And as a second good result, we have seen the emission of delayed fluorescence in the case of the DHU binary phones that after this quantitative energy transfer, something that to my knowledge, has not been reported yet. And by applying femtosecond transient absorption, we have seen again that these energy transfers should be quantitative and happens in the ultra-fast time scale, and together with pump-probe anisotropy experiment, maybe accounts for a coherent energy transfer within those nanoparticles. As perspective for the future, we for sure have to get into the large data set we have acquired, especially in the pump-probe anisotropy experiments, and maybe we will get a deeper insight on the overall behavior by performing bidimensional electronic spectroscopy with some collaborators. For now, I want to thank my collaborators at University of Bordeaux, as well as at the Indian Institute of Technology of Indore, my research group at University of Perugia, and of course, you all for the kind attention.